Okay, hello to all of the participants, and it's a pleasure for me to be here today, and my special thanks for organization of this scientific webinar and conference. So I am Foad Ghasemi from Department of Physics of University of Kurdistan from Iran, and my talk is about the MOS2RGO-based photodetector for in situ gas sensing. It's a kind of sensor, optical sensor, actually. Let's see the content. I will briefly talk about graphene discovery and then move to the two-dimensional materials, mainly TMDs, a kind of one kind of the 2D materials. I will talk about the preparation and also application of TMDs, mostly molybdenum disulfide, and then I will move to 2D based sensor gases. I will talk about the challenge and issues in this kind of sensors, and then go to my results on material preparation, characterization, and sensor fabrication. And finally, I will talk about sensor performance and comparison with others reports in the literature. Single layer graphene was theoretically predicted in 1947, but it takes few years to finally be experimentally discovered in 2004 by Nazarov and Gaim. And since then, there are a variety and very interesting research on the graphene and has been reported so far. But the good news is that the graphene is not alone. Today we are many different 2D materials beyond graphene, especially the TMDs or metal oxide, or also perovskite structures that are suitable mostly for solar cell capturing. And today 2D materials cover all electromagnetic spectrum from insulating to the metal property. For example, we have a boron nitride with high energy band gap. It's a kind of insulator, and graphene as a metal. And between them, we have many different 2D materials like TMDs and black phosphorus as a tunable band gap structures that bring UV visible and also in the UV visible regions applications and properties. So TMDs, or transition metal dichalcogenides, is a kind of 2D materials composed of transition metal atoms like molybdenum or tungsten, and sandwiched between two layers of chalcogen atoms like sulfur. And we have many different TMDs, like the most important you are molybdenum disulfide, MOS2, and tungsten disulfide, WS2. But we have others TMDs that are important also. And some methods for preparation TMDs are, for example, the intercalation or solvent exfoliation. They use the sonication or intercalation to peel off the layers, mechanical exfoliation using tape, chemical vapor deposition methods, or even thermal evaporation process, and other methods that used to prepare the MOS2 or TMD layers, or even at a wafer scale size. And also there are very different applications for these kind of materials. For example, they use in transistor for fabrication transistors because they provide high electron or high carrier mobility with on-off switching, with a considerable good on-off switching. They use as a photodetector for the detection light. They have a good interaction with light, and also as a gas or biosensor due to their large surface area, or even at energy storage devices. because they also provide large surface area and also good conductivity, electrical conductivity. That are both are more important for energy storage devices. So today my talk is about the MOS2 graphene-based nitrogen dioxide gas sensor. But there are some variety reports on this kind of structures, but there are some issue in this kind of structure. Here is a WS2 graphene sensor for NO2 gas sensor. As you see that the device at room temperature show poor recovery time. It's a main problem with this kind of sensor. So for improve and for solve this kind of issue, mostly prefer to work in the higher operating temperature, for example, near 200 Celsius. And also here is another report, MOS2 graphene sensor. As you see that they also use the higher temperature. At a higher temperature, the better recovery time can be seen. But the problem is when we we heat up the sensor, we lost the sensitivity compared with the room temperature. So there's a trade-off between these two parameters, and sometimes if you want a better recovery time, we lost the sensitivity of the sensor. So one option is, instead of using thermal energy, we use the light irradiation. And there are some reports on MOS2 structures that work under illumination. Here is the sensor under dark state, and after illumination to the light, the sensitivity and also the recovery time is improved considerably. And also another reports for molybdenum disulfide under UV illuminations, we can see that under UV illumination we have a higher sensitivity compared with the room temperature, or even compared with the 100 Celsius operating temperature. So it's interesting a suggestion for fabricating a new sensor. So my result in this kind of sensor, I have prepared 3 different materials, MOS2 with solvent exfoliation methods with probe sonication, and also graphene oxide with a modified Hammers methods. It's both a chemical process to prepare this kind of material. And also we grow vertically aligned carbon nanotubes that serves as an electrical contact for graphene and also for the molybdenum disulfide. Here is the TEM image of the vertically aligned carbon nanotube, TEM image of the carbon nanotube, and also the SEM image. And graphene oxides, the TEM image and also the diffraction pattern show the crystalline structure of the graphene oxide, and the SEM image of this deposited graphene oxide. And also we prepared the molybdenum disulfide few layers, both TM and SCM shows the structures and good formation of this structure. And also we use Raman and AFM measurements to characterize our layers. Both Raman and AFM shows the good formation of these layers. Their AFM show the thickness around 13 nanometers of graphene oxide, and also the AFM also show the 1 to 2 nanometers thickness of the MOS2. So another characterization is UV visible and Raman spectroscopy for the hybrid structure. As you see that the graphene oxide has a absorbance around the UV region. We use thermal reduction to reduce graphene oxide Reduced graphene oxide is a kind of conductive materials compared with the GO that is insulated. And there is a little shift in the peak of the UV visible in the UV region. For individual MOS2, we have some peaks, mostly around the UV visible. And the hybrid structure of MOS2 and RGU shows the good combination of the both peaks and the good formation of the hybrid structure. Also, we use the Raman for the graphene and reduced graphene oxides, that we show that the ID or to IG ratio decreases, and is a sign of the reduction of the GO2 reduced graphene oxide. And also the hybrid structure show peaks for both materials, MOS2 and also reduced graphene oxide. To fabricate our device, we first thermally gross silicon dioxide and silicon, and then using sputtering, we deposit nickel, a thin film of nickel around 10 nanometers and substrate, and then using photolithography process, we pattern this kind of layer. Nickel serves as a catalyst for growth of carbon nanotubes. Using plasma-enhanced chemical vapor deposition, we vertically grow the carbon nanotube, and then we drop cast the layer of our reduced graphene oxide, a large layer of reduced graphene oxide over the channel, and then drop cast the molybdenum disulfide on the graphene channel. As you see, there is some dots that's referred to molybdenum disulfide, and also the RGU is enough thin that we can see the carbon nanotube behind them, and also the cross-sectional image show the carbon nanotubes and a layer of RGU distributed over the channel of the source drain structure. We test our contact, two kind of contact, vertically aligned carbon nanotubes and also gold contacts to show the electrical performance of our device. In the case of carbon nanotube, because the height of carbon nanotube is around 2 microns, so we have a kind of suspended RGU layer compared with the IU structures that's graphene is on the channel and the oxide layer. And electrical measurements show that carbon nanotube contacts show the better electrical performance and lower resistance, electrical resistance. Here you can see that in the case of carbon nanotube, we have about 0.1 electron volt Schottky barrier. And in the case of gold, it increases to 0.5 electron volts. So we predict that the vertically aligned carbon nanotube provide better electrical performance for our devices, since both structure, graphene and also vertically aligned carbon nanotube, both contain carbon atoms that can bond together and form a better electrical connection. Before adding molybdenum disulfide, we test the optical response of the sensor, and we find that a poor optical response can be seen for the graphene and the vertical carbon nanotube, even at high optical power intensity. That's in order to improve it, we added molybdenum disulfide layer. As you can see, the schematic of the sensor, we added molybdenum disulfide, drop cast it on the RGU layer, and then we test the optical response of the sensor for various wavelengths, laser wavelengths at the same optical power. The switching response of the sensor to the light and also under dark conditions, it can be seen here for the different laser wavelengths and even for the different power intensity of light. That's our sensor shows a good optical performance under light. Those parameters are important are responsivity and also response time. So we conduct our test for achieving these two parameters, responsivity versus wavelengths for both devices, vertically aligned carbon nanotube contacts and also sensor with IU contacts, shows that in the case of carbon nanotube, we get higher responsivity, and the peak around the 400 nanometers. It refers that we have a higher photoresponsivity around here. That is totally compatible with our UV visible structures. That's, we have a here, and we see that around here we have a better responsivity compared with a point here or other points. So it's due to the good formation of our hybrid structure, and also the responsivity versus power intensity of light shows the had better performance for vertical and carbon nanotubes, and also we have a fitted line that showed that we have a 6.67 for the vertical aligned carbon nanotube. That's it tell us about the good formation of the structure, and also tell us that our structure has a good optical performance and higher efficiency conversion of photon into the electrical signal. The time, the response time and time result measurement also shows that with the vertical aligned carbon nanotube contacts, we have a better response time and also recovery time. That's it's maybe due to the lower electrical Schottky barrier between graphene and carbon nanotube. So in the next part, we test our device for detection of nitrogen dioxide gas molecules. In the case of RGO and carbon nanotube, we test the sensor in dark condition and also under laser illumination. The blue line is under laser illumination, and as you see that in the there is no significant difference between two structures, and in both we can see the poor recovery time. But when we add molybdenum disulfide and test again the measurement, we see that in the case of adding molybdenum disulfide, we achieve a higher sensitivity for the sensor, and also a good recovery time compared with the dark conditions. It's a recovery time about 150 seconds, so that is very reasonable, and also a good recovery time compared with others reports. And we also test the sensor under different power intensity of light, the responsivity. So the sensitivity of the sensor for different measurement conditions. The first one is under dark in air ambience, and when we test our sensor in nitrogen ambient, we get better responsivity, sensitivity, because in this kind we don't have oxygen or water vapor molecules that can decrease the sensitivity of the sensor. And under laser illumination, the higher sensitivity is achieved. The sensitivity compared power intensity showed that with increasing the power, the sensitivity also increased, but at the one point it's around 5 microwatt. By increasing the power, the sensitivity decreases. We believe that is a kind of saturation in the sensor, in the materials. That's there is no response out there. It's kind of saturation with absorbing light, and so applying more power intensity doesn't actually change the sensitivity, and also decrease it. The dynamic response of the sensor in three conditions, nitrogen ambient, air ambient, also under laser illumination, show that in the case of laser illumination, we have a better response, better sensitivity, and also better recovery time compared with both other conditions. And also the switching performance of the sensor showed a good stability of the sensor and the introduction of the nitrogen dioxide gas into the sensor. We also test our sensor for 3 different gases. Ammonium also we test it, and we measure our results with other gases also. In the kind of ammonium, you can see that we have a better responsivity compared with the dark state, and also better recovery time mostly. As you can see that here we have a positive sensitivity compared with nitrogen dioxide, that it has a negative sensitivity. It's due to the this fact that in the NO2, with introduction of the nitrogen dioxide, the current in the sensor decreases. But in the case of ammonium, the current increase in the sensor after introduction of ammonium. Also for 2 other gases, oxygen and also ethanol, we check our sensor both in under laser illumination and also in dark condition, and we see that in all cases under the higher sensitivity can be achievable under laser illuminations. So let's talk about the detection mechanism of this sensor. So we fabricated a kind of sensors, it's a kind of hybrid structure. We use molybdenum disulfide as active optical materials in our sensor. By irradiation, the electron hole pair generated in molybdenum disulfide, and the electron affinity of MOS is around 4 electron volt. And also work function of graphene, reduced graphene oxide, is around 4.9 electron volts. So when electron hole generated in the molybdenum disulfide, electron can move into the, can transfer into the RGO layer, and also the lower work function of typically around carbon nanotube lets electron easily go to the contacts and then extract from the sensor and use in the circuit. But the mechanism for sensing the nitrogen dioxide is based on the very simple fact that when we do not, when the sensor is not irradiated by laser, the oxygen or vapor molecule in the air ambient can accumulate on the hybrid structure and also occupy the active sites of the molybdenum disulfide or RGO. So they can occupy all this kind of active site and decrease the sensitivity of the sensor. But when we irradiate, when the sensor is irradiated by laser, electron hole generation cause that this kind of active site be released, and we have an active site that are now free, and they can react with the nitrogen dioxide molecules. So in this case, we improved, the sensitivity is improved. And also in the recovery time, also the irradiation energy can provide energy for releasing the occupied sites with nitrogen dioxide. And also we compare our result with other reports with different 2D structures. As you see that most of them work at higher operating temperature, or even those that work at room temperature suggest lower sensitivity. But in our cases, we use room temperature as an operating temperature, and also higher sensitivity and better recovery time for our sensor. Thank you so much for your attention, and if you have any question, please, I'm here to answer.
Thank you, Professor Foad, for your wonderful presentation. Yeah, we'll leave some time here. If anyone have any questions or comments, go ahead and please ask.
Anyone? Yeah, I have one question.
Yeah.
Yes.
What is the signal to noise ratio in your case? Because you are talking about sensitivity of the system, right?
Yes. Actually, we haven't measured the signal to noise, but actually we haven't measured it. But if you see that in the case of switching, after irradiation, we mainly have for example, around 1.5 microampere increasement in the current after irradiation compared with the darker state. That's so we haven't measured the signal to noise, but this increase because we have a good increasement of the current after irradiation. We have a good signal for measuring the sensitivity of our sensor.
So another question, because I have a curiosity, because your current is very small, it is a microampere, right?
Yes.
And microampere current is always suppressed by the external noise.
Okay.
Because noise is always higher in the laboratory.
No, we also have some sensor that we can easily also measure the nanoampere current. And
you can measure nanoampere current. So for that, are you using lock-in amplifier or some other type of gadgets for amplification and then rectifying the inherent noise of the system and then for the measurement, something like that?
Yes, I agree with you that maybe the signal to noise, also the noise here is important, but actually we haven't measured it, and maybe in our future work we should pay more attention to your suggestion. Thank you so much for your suggestion.
Thank you. And last question, because NO2 you are talking, and NO2 has very good absorption at 532 nanometers, right?
Yes.
So what is the reason selecting ultraviolet, 375 or 405 or 450 nanometers, when you can get very good signal at 532 nanometers? And NO2 is having very strong, vibrations of this thing.
Yes, but actually for this kind of 2D materials have a good interaction with light, and so we can they show a good response to the light. And sorry, I forgot your questions.
No, I am asking the reason for selecting ultraviolet radiation, because 530 itself is able to provide you very good signal.
Yes, actually.
In case of NO2.
Yes. It's both. You say it's correct, because in the kind of UV, as you see, let me again show the laser point. We actually doesn't have a optical source for here, and also most reports prefer to work on the UV region. And if you look through the literature, most of the works reports the UV. Here are actually most prefer to work on the UV region, because it provides higher energy, and also higher energy for recovery of the sensor, and also higher energy for improving the sensitivity.
You meant to say that intensity is very high in case of UV.
Yes. Intensity here is high, and is if you see that might overtest for lower wavelengths. I have to show here. Okay. Yes, for lower energy wavelengths, we find lower sensitivity. The radiation energy is important for us. Improve the sensitivity. You're welcome. Thank you so much.
Thank you very much.